Hello. Uh, in the second experiment of VLSI Design Lab, we will be learning about sequential circuits. So, the sequential circuit, the basic of all the sequential circuits starts actually with latch and flip-flop now. I don't know whether you remember learning about latch and flip-flop from your digital electronics or not. Let us just remember how it works. For example, in latch or flip-flop, there will be a clock. We'll be learning that these in theory as well. So there is a clock, and suppose there is an input called data. So this is our excuse me. So this is our data input, and now the output Q. If it's latch means level triggered. That is, the output will be equal to input only when clock is high. So when we see when clock is high, the output will look like this. Now, at this point, the clock becomes low. When the clock is low, the output retains its value. Again, when the clock is high, we, we can see that it will follow the data. The data looks like this. Again, when the clock is low, the sorry, when the clock is low, the output will keep the data as it is. Keep the output will retain its value. Again, when clock is high, it will see how the data is and follow the data. And when the clock is low, it will keep the data as it is. That is, when the clock is low, when the clock gets to low, if the output was 1, it will remain 1 till the next time clock gets 1 high. Or output if it was 0 will remain 0 till the clock cycle gets high. So that is how latch works. And flip-flop is edge triggered. So this is level triggered. Flip-flop is edge triggered. That is, it only works on edges. Let us suppose it's work on positive edges. That is when output goes from 0 to 1. So let us just assume that we are designing, we are talking about a positive edge triggered circuit. Now what it does is, at the positive edge, notices or measures the value of D or data, and it keeps that data till the next clock edge. In the next clock edge, it again sees the value of data. The value of data is 0, and it will keep the data till next clock edge. In the third clock edge, it finds that the value of data is 1, so it will turn the output is equal to 1, and it will keep the output is equal to 1 till the next positive clock edge. So this is how flip-flop works. The latch is level triggered and flip-flop is edge triggered. Now, you'll be learning about these things in details in your theory. This is not our primary concern. Our primary concern is how the circuits of latch and flip-flop are made. Now, the latch are made with the help of NAND gates. Uh, the circuit diagram is kind of like this. Here we have clock. Here we have data. So this is our data, this is our clock. Here we have Q or output, sorry. Here we have Q, that is output, and here we have Q bar. This is a latch. So if we turn this into a block, what would happen? We will have an input of D, an input of clock, and an output of Q and Q bar. Now, using this latch, we can make a flip-flop. So these two are, say, L, these two are latches. The Q or the output of the first latch goes into the input of second latch, and we have Q here, Q bar here, and here here we have data, and we have clock. We put the clock to this latch and we put an inverted clock to this latch. If we do this, this thing that will be created will be flip-flop. So uh, as I said, flip-flop is edge triggered. So this circuit over here will be edge triggered, and latch is level triggered. That is, this circuit will be level triggered. So what we need to do at first is we need to design the latch and flip-flop. So the basic element of the latch or flip-flop is the NAND gate and the inverter. So at first we have to design the NAND gate and inverter. So so we open our DSCH and we design a basic NAND gate. We can design it using PMOS and NMOS. So if I remember right, in NAND gate we have two PMOS in parallel and two NMOS in series. We have a VDD and a ground. So this is our basic NAND gate. We connect the lines through wires. And connect this to. Okay, now we'll declare a button here and a button here. Let's name the buttons as B and A, and we'll have an LED to see the output. And let's name the LED as O. So what happens is, if we simulate it, we can see that 0 0 will give 1 as output, 0 1 will give 1 as output, 1 0 will also give 1 as output, and 1 1 will give 0 as output. So our NAND gate is working. After we see it is working, we have to save this file. Save as, we name it AAA underscore NAND 2, just naming it. Okay, and the file, the position of the file is really important. In my case, this is fall 2020. So this is the file you'll be saving is the file from where you have opened the DSCH file. So I'm saving it here, AAA NAND 2. Then the next thing I do is I click schema to new symbol, and here we can see the symbol is A and B as input and O as output, and we press OK. It looks fine. And let us see. Now let us insert user symbol. Name was AAA underscore NAND 2. We select that and put it here. So let us see if it works. If we put an LED here, a button here, and a button here, we can see if we put run, 0 0 gives 1 output, 1 0 0 1, both of them 1 1 1 gives 0 output. So the NAND gate is working. So we have created the symbol of NAND gate. Now we create the symbol of inverter. That is really easy. A PMOS connected to an NMOS, ground with the pull down network, VDD with pull up network, button as an input, and we wire it like this. We bring a wire here. We connect LED to the wire. So let's name LED A, not A, and let's name the input as A. Now if we run, when the input is 0, output is 1, input 1, output 0, the inverter is working as it's supposed to. We again save it, AAA underscore not. So after saving it, we select this, and the symbol is here. What I'm doing is, if I place this, the symbol is very widened. If I press this, the symbol is shrunken. So it's up to you. It's just that it's related to the aesthetics of things. You don't actually need to change it, whatever it is. So I press OK and I insert symbol AAA underscore not sim. Press OK. So we put a button as an input and an LED as output. And when we simulate it, see, the knot is also working. So we have the basic blocks working. Now the first thing that we'll do is we will build the latch. So for building a latch, we open a new window. So for latch, we'll be requiring NAT, NOT and NAND. So we use user symbol a underscore NAND2. So this is one NAND. As we can see in the diagram, we will be needing 4 NAND gates. So what we can do is, this is our copy option. We press this and we drag it over here. We will have the copy of this made. Wherever we want to place it, we take it there and click it. Similarly, I can copy this again. So our 4 NANDs are there. Another thing that will be requiring is NOT, symbol of NOT. So the symbol of NOT is also here. So let us make the connections. Connections are really easy. This output goes to this input. We move it a bit. This output goes to this input. This goes here. This goes here. We have an LED here, which we'll be calling Q. We have another LED here, which we'll be calling Q bar. That is not Q. And we connect this. And so we have a button here, which will be our clock. We name it clock. And we have another button here, which will be our data. So we name it D. Okay. So the latch should be working. So I turn it on. At first we need to give a pulse so that it works. So when the clock is 0, data is 0, Q is 0. If we change the data, the value of Q does not change. When the clock is 1, when we change the value of data, the value of Q changes. So let us take a value of Q, say Q is equal to 1, that is data is equal to 1. Then again, when we switch off the clock, if we change the value of data, the earlier value of output remains. The value of output does not change. So this over here is a latch. That is, when clock is 1, the input is mapped to output. When clock is 0, the output retains its previous value. So our latch is working. What we can do is we can save it at first. I'm naming it AAA underscore latch. I'm saving it and then I'm converting it into a symbol. The inputs are B and clock, outputs are Q and Q bar. So I prefer Q at the top and Q bar at the bottom. So here we have 2 and 1. I type 1 here and 2 here. If you do that and you press, the Q would be at the top and Q bar would be at the bottom. Just the aesthetics of it, we don't require it to do this. It's just a simple beautification and nothing else. So okay, our latch has been designed and latch is working. The next step is designing a flip-flop. So this is our latch. We will learn in the theory how the circuit actually works, but we have already demonstrated that it is an edge-triggered circuit. So that should be enough for now. And you have learned about latch in your digital electronics. If you don't remember it, just go through with it or wait for the theory lecture. It will be covered. Now let us take a new window. From the new window, we insert our latch that we made. There is one latch we'll be requiring. If you look at the circuit diagram, we'll be requiring two latch and a NOT gate. So we copy it, copy this latch, bring it here, and insert, choose a symbol, AAA underscore NOT symbol. Okay, we put the symbol here. Now the latch should look like this. This goes here, this goes here. The Q of the first latch goes into the D of the second latch. Uh, there will be a button here which is our T or data button. There will be another button here which will be our clock. Okay, and there will be LED here which will be Q, and there will be another LED here which will name Q bar, not Q. One thing is to be noted that you see I'm putting a button as a clock, but you can use here we have clock, you can use that as a clock as well. I'm using the button as a clock because it gives me more uh, it it lets me control the speed very easily. That is, I can show you whether it's level triggered or edge triggered very easily. You'll soon see how. So the circuit is here. The circuit is similar to the circuit that we made here, and let's work with the circuit. Let's run the simulation. At first, nothing will be shown. We have to enter a clock at least once so that the output is resulted. Now, what happens is, see, when the clock is 0, if you change the D, the value does not change. When the clock is 1, if you change the value of D, the value does not change again. What happens is, whatever the value of D is, when the clock is turned from 0 to 1, the value will, as the output will attain that value. For example, D is 0 and clock is turning from 0 to 1, so output is 0. If D is 1 and clock is now turning from 0 to 1, the output is 1. That is, output only works at the positive edge of a clock. When there is no clock edge, output will not be mapped to the input, and again when there is no clock edge, output will not be mapped to the input. That is, we can switch the clock on and we can turn the data on and off as many times as required, but the output will not be changed. Output will be changed if and only if the data is changed at the positive edge of a clock. So if I now press the clock, it will have a positive edge and the data it will see is 0 and the output will become 0. So we understand that this is not level triggered because when the clock is 1, the output is not changing. When the clock is 0, output is not changing either. Output change when clock goes from 0 to 1. Again, output does not change when clock goes from 1 to 0. When clock goes from 1 to 0, output does not change. It only changes when clock goes from 0 to 1. So this is our flip-flop. Now we save this. AAA underscore FF. So this type of flip-flop is called D flip-flop. We make sorry. So this type of flip-flop is called D flip-flop. Save as. Okay, this type of the error that you're seeing, this type of error occurs when you when you save a file without stopping the compilation, and it will not work anymore. We'll have to close it and we'll have to reopen it. As long as we don't reopen it, the DSCH will not work. Whatever it is, now let us open the file again. Hopefully this time it will work, or otherwise we have to make it again because of the mistake. So AAA underscore flip flop, we open it, we run. So flip flop is working now. So file, we save it again, and we convert we do the same thing with it. That is, again I'll be putting the Q at top and Q bar at bottom. So this is our flip-flop. The Q at top, Q bar and bottom, we have T and clock. So this is H triggered. We save it. So we now have a symbol for flip-flop. So whatever we are doing, we want to design a circuit that would be, suppose we want to design a counter or a ring counter, a shift register, sort of these things. If you look into internet and go into details, you'll see that all of this will require the use of flip-flops. Now, only flip-flop in these cases will not be uh, will not be enough, because suppose we want to make a counter that delete it. We want to make a counter that counts from 2 to 10. Suppose that is, it counts from 1 0 to 1 0 1 0. So what happens is, when the output is 1 0 1 1, what it does is it changes the output to 0 0 1 0. That is, it sets this and it resets all the other 3 bits. So I'm just giving you an example. When the output becomes 1 0 1 1, it sets one of the bits and resets the other. It can be like this. Suppose it can be 3 to 10. So 0 0 1 1. So what happens is, when it reaches 1 0 1 1, what would we do? It would set these 2 pins and reset these 2 output. So this is how actually the thing works. So that is, in our flip-flop, we will be needing two operations: set and reset. So how does our flip-flop work? Our flip-flop works is, if there is a positive clock edge, then what happens is, the clock edge is positive. What it does is, uh, it connects the data to the output. At the positive clock edge, it connects data to the output. So we want this operation, but what we want to do is, if set is equal to 1, it will turn Q is equal to 1 at the positive edge of the clock. And again, if reset is equal to 1, it will turn if reset is equal to 0, it will turn Q is equal to 0 at the positive edge of the clock. So what we want to do, we want to design a system that in which, if reset is equal to 0, the output will be equal to 0 at positive edge of clock. If set is equal to 1, the output will be equal to 1 at positive edge of the clock. And if reset is equal to 1 and S is equal to 0, at that point the output will be equal to D, or the data input that we have. So we are giving the highest priority to reset, second highest priority to set, and lowest priority to data. So when reset is exerted, we don't care about any other things. The output will become 0 at the next positive edge. And if reset is not exerted, that is, reset is 1. And then if set is exerted, then we do not care about the data and the output would be 1. If reset is not exerted, that is, reset is equal to 1, and set is not exerted, that is, set is equal to 0, then what do we do? Then we connect the output to the data. So how we can do that? We can do that if we make this pin D act in such a way that whenever we press the reset button, this D, that is the flip-flop that we have, suppose this is a flip-flop, so this is a data, then what happens, what we can do is, whenever we press reset, this will become 0. Whenever we press set, that is, whenever reset is 0, we'll put 0 in this pin. Whenever set is equal to 1, we'll put a 0 in this we'll put a 1 in this pin. And if none of these conditions are active, then whatever the value of D is, that goes into this pin. That is, this is our data pin. Our clock and Q bar remain as they are. So if you look into the lab sheet, if you look into the lab sheet, it has been described in the lab sheet very well. We can look at the truth table. In the truth table, let us see if reset is 0, highest priority is reset. If reset is 0, output is 0. So the first 4 outputs are 0 because resets are 0. If reset is 1, the second highest priority is set. If reset is 1, then we will see the set. When reset is 1 and set is 1, the output is 1. So reset 1, set 1, we get output 1. When reset is 1, set is 0. That is, reset hasn't been exerted, set also hasn't been exerted. At that point, the output will be equal to data pin. That is, the data is 0, 1, so the output becomes 0, 1. So if the variables are set, reset, and data, the equation of the output becomes, for this it will become reset set bar D, it will become reset set d bar, it will become reset set d. So if we simplify it, we get this equation, reset set bar d plus reset set. So if this is the equation, we can actually use this equation, or we can actually build up this equation. So our equation is reset set bar d and reset set. So if you want to use, if you want to build up this equation, what we need our reset. So let's name it RST. We need a button called set ST, SET, and we need another input called T. We have 3 inputs, D. Now the logic is, again if you look into it, the logic is reset set bar D. So what we do, we have 3 PMOS in parallel. We have 3 PMOS in parallel. So reset set bar D. The first PMOS will have reset connected to it. The second will have set bar, and the third will have D. So let us connect the third one first. And since it will have set bar, we insert symbol AAA underscore not. So by using the inverter, we have the set bar with us. So now we connect it. So here we have reset set bar D. The next, with this we add reset into set. So with this, in series with this, we will have 2 PMOSes. The gate of one PMOS would be reset, since it is reset into set. The gate of one PMOS would be reset, and the gate of other PMOS would be set. Now obviously, since reset and set are multiplied, these 2 PMOS will be in parallel, and since reset into set is added to the reset set bar D, so it would be in series. So I'm connecting this, and at the top I'll have a VCC. Now this is the pull-up network. So if we want to convert it into pull-down network, we'll have here, we have 3 PMOS in series, so we'll have parallel, so we'll have 3 PMOS, 3 NMOS in series. Again, here we have 2 PMOS in parallel, so we'll have 2 NMOS in series. And this entire thing will be, since these and this is series, the entire thing will be parallel. So what we do is we connect this. I think it's parallel. So first thing is reset set bar. So we connect reset here. We connect set bar here. We connect D here. Reset set bar D. The next thing here is reset set. So here we have reset that we can connect here, and we have set that we can connect here, and the pull down and pull up network would be connected, and the output of it will obviously pass through an inverter. So we have an inverter available. Uh, so what we do is we use the line here and we put an LED here. So what happens is, and another thing is we have, so here the output would be data input of the flip-flop. So the circuit has been made. Let us see if the circuit works. Let us just run. So our condition is if reset is 0, no matter what we do, the output would be 0. So we are changing set, but the output remains 0. Now if reset is 1, the output will be 1 if set is 1. The value of D does not matter. The output would be 0. Output would be equal to D if set is 0. Now here set is 0. D is 0, output is 0. D is 1, output is 1. So if we look very carefully into our truth table, we will see that our operation here is completed, and what we needed, we have derived it. So this is a controller that will control the set and reset operation. So we are naming it AAA underscore control. And again, what we are doing is we are converting it into a symbol. And what we can do is we can create new file. We use AAA control and we insert AAA FF flip-flop. So we insert AAA flip-flop. So what will happen is we have an input called set. We have another input called reset. RST. We have another input called data. D. And we have another input clock called the clock. Sorry. So okay. We are having these 4 inputs and we connect the D in with the D and we will be having 2 outputs. So what we developed here, we developed a set flip-flop which will have the set reset operation. We named the first output as Q and the second output as Q bar. The set reset operation. So the design is completed. Firstly, the output would be floating. This ash color means floating. When we change the clock, the output will start having its value. Now, what we need to do is we need to see when the reset is 0, the output is 0. No matter what the value of set and D is, the output will never become 1. So if we turn reset 1 and set 1, the output is 1. Even though the value of D changes, the output does not change. If reset is 1 and set is 0, then the output will be following D. And everything will be occurring only at the positive clock cycle, the positive clock edge. So this is our flip-flop, D flip-flop with set and reset operation. We save it, save as AAA underscore D FF underscore SR for set reset. So now what I want to do is, the sides there, here left is L. If we put it as U, it would go to top, and if we put it as D, it would go to bottom. And let us select one here. So what I did is I kind of modified the pin numbering so that it looks like this. You don't need to do this. This is just an example. It looks better. There is nothing extra benefit associated with it. So after we are doing this, we save it. Maybe what we can do is we can delete the entire thing. We can insert the, so this is our DFF, that is D flip-flop, which has both set and reset operations available. Now, what happens is we'll be making a Johnson counter uh, using the flip-flop that we have just developed. So Johnson counter works like this. Initially, we are making a 4-bit Johnson counter. Initially, let us suppose the 4 bits is 0000. Then what happens is it will give at in the next cycle all the things will be right shifted and 1 will be added at the left. Next is 1100. Next is 1110. Next is 1111. When all the outputs are 1, what will happen is now 0 will be coming from the left side, that is 0111, 0011, 0001. So the counting will shift with every clock cycle, the counting will shift in this direction. Now, what happens is if we look more closely, the first bit becomes the not or the inverted value of the last bit. First bit is the inverted value of the last bit. That is, if last bit is 0, first bit is 1. That is actually the direction that I have shown is not correct. After each clock cycle, the first bit becomes inverted value of the last bit. 0 is inverted to 1. 0 is inverted to 1. Again, 1 is inverted to 0. The last bit, this 1 is inverted to 0. Again, this 1 is inverted to 0. So, first bit becomes inverted value of the last bit. This is how Johnson's counter works. Now, I'm not going into details of the details of the circuit. You'll find this circuit. You have learned about this circuit in your digital electronic courses, and you'll find this circuit readily available in internet. You can search Google as Johnson counter, and you'll find something like this. It is not really difficult. What happens is, if you look closely, we have 4 D flip-flops. The output of the first flip-flop is connected to the input of the second. Similarly, all the outputs of the flip-flops are connected to the inputs of the next flip-flop, and the input of the first flip-flop is connected to the inverted output of the last flip-flop. So if we want to design it, what we would do is we would just open DSCH, then we'll insert our user symbol of DFFSR. So we need, as it is a 4-bit flip-flop, we need 4 of them. So we are using 4 of them. Now what happens is, we'll see why we require the why we'll be requiring the set and reset options shortly. So our circuit is like this. Circuit is like this, and all the clocks are mutually connected. Okay, so we are connecting all the clocks mutually. So this works, there is no problem. But what happens is, the biggest problem is here we do not have any input or output. Then what happens, at initial position all the points are floating. If all the points are floating, the value of Q is floating, Q bar is floating, everything is floating. So this input is letting floating input, and as a result it will give floating output, and everything will be floating. So since the Johnson counter starts from 0000, we have to devise a mean by which we can input the 0, 0, 0, 0, or we can input 1, 1, 1, 1 as well. It's up to us. So that's why we need the reset. That is, if we do not have either reset or set, then what happens? The output will always be floating. So we require either of them. So uh, since we have the luxury of using both, we have the both of them. So we'll be using both of them. So we have a button called clock here. We put another button for reset here. We put another button for set here, and the circuit is pretty much it. Only thing left are LEDs. Here we put the first LED, we put the second LED here, third LED here, and last but not the least, the fourth LED here. Um, okay, all the LEDs are done. Now our circuit is complete. If we run, at first reset is 0. When see everything is as you can see, everything is floating. The floating thing will end as soon as we press the clock. Everything is 0. It is to be noted that the floating has gone only because reset is exerted. Let us stop for a bit, run the simulation. If reset hasn't been exerted and set also hadn't been exerted, then everything would have remained floating. So that is, if we did not have reset and set options, the output will always remain floating. As a result, what we need to do is we have to exert either reset or set and then use our clock. So we have 0, 0, 0, 0. Now we have to remove the reset, obviously, because as long as reset 0, the output would be 0. Now for the first clock age, it becomes 1, 0, 0, 0. At second clock age, it becomes 1, 1, 0, 0. Third, 1, 1, 1, 0. Fourth, 1, 1, 1, 1. Fifth, 0, 1, 1, 1. Sixth, 0, 0, 1, 1. Seventh, 0, 0, 0, 1. And last is 0, 0, 0, 0. And it will continue like this. So this is how we can design Johnson counter. In this method, we can design any kind of counter. We can design a BCD counter, 2 to 10 counter, 4-bit counter, up-down counter, ring counter, shift registers. We can design all the sequential circuits using this. In the reports, you'll be requiring to design some sequential circuits. It's very okay if you do not know how, if you do not have the circuits that or do not know where the circuits are. You can search Google and you can easily find out the logic behind those. And if you still face any problem, you can contact me and I'll be trying to solve your problems. That's all for this lecture. In the next lecture, we'll be learning about microwind, which is a layout